So basically, the only thing I need to do in this slide, therefore, is to correct this. It's not just transposed. So this has to be, because our matrices are generally complex, so this will have to be Hermitian transpose, which means that we take standard transposition and add complex conjugation on top of that. Okay? Is that clear? Good. Well, all good, but what I would like to do is now see if it actually works. So, and if it does, how it works. So I will go back to this very example and see if this theory will help me to determine the k value. So remember how we did that. We looked through this, we solved this problem formally, and then we realized to avoid that to avoid the division by 0, we need to choose k equals 4. Okay, so that's what it was. And the problem was, at this stage, the problem was that, well, computers, they don't know how to deal with these formulas if denominator is equal to 0, no matter what. So therefore, you would need to somehow explain computer, all right, if you see 0 at this particular location, don't try to divide by it. Okay, so, and that's nightmare to program, logical nightmare. You cannot talk to a computer and tell them, all right, do this all the time, except when this happens, then you do something else. Okay, so AI only comes into play now, so definitely 10 years ago, 2 years ago, it was not there, so you cannot tell that computer, this to computers. So therefore, we need to come up with a sort of completely generic idea, generic implementation of whatever we are doing, so that we can explain this to a stupid machine. Okay, machines at the time were stupid, and they're still stupid, probably will remain stupid, but in a different way. So I'll just create an extra slide. Let me just go through the ingredients. So in that example, L was equal to sigma plus 1, 1, and 2, and minus 1. Okay? So this, what I am referring to is this problem. So L is the combination of these two matrices, right? It is sigma plus 1, 1, 2, minus 1. So that's what L is. Agree? So, and I just copy it and see what happens, because now I'm formally trying to apply that theory of adjoint. So this is my matrix L. Adjoint is going to be transposed plus conjugation. So everything here is real. Maybe sigma is not real in principle, but in our case, even sigma is real. So in this case, it's just pure conjugation, pure transposition. Agree? So therefore, L dagger is going to be equal to sigma plus 1, 2, 1, minus 1. Agree? The adjoint eigenvalue problem is going to be this. It's generic, meaning that sigma plus 1, 2, 1, minus 1 x dagger y dagger is equal to 0, 0. Agree? So that's what the problem is. So W dagger is equal to X dagger, Y dagger. Okay? That's what we have. Now, right-hand side is 0. We don't want this to be 0. So therefore, we must insist that the determinant of this matrix is equal to 0. Agree? So therefore, minus sigma plus 1 minus 2 is equal to 0. That's the determinant. Agree? So what's the value of sigma? What is it? So minus sigma minus 1 minus 3 is equal to 0. So sigma is equal to minus 3. So it's the same. So, and this is not a surprise because there is a property. So eigenvalues of the transposed matrix and original matrix are the same. They must be the same. Okay? And in this case, it's a real this is real case, so therefore they, if it is complex conjugate matrix, then we would get complex conjugate eigen value. But in this case, everything is real, so complex conjugate is equal to the original quantity. So therefore, it is not a surprise. So, and that means that we don't really need to solve a joint problem to find eigenvalues. Because eigenvalues are guaranteed to be the same. At most, they will be complex conjugates. Okay? However, we still need to find eigenvectors, so this W dagger, because that is important. We will need to use it later on in the dot product. So, therefore, we still need to solve eigenvector problem. Okay? So, therefore, if sigma is equal to minus 3, I will get, substituted back, I will get minus 2 2 1 minus 1 X dagger Y dagger is equal to 0 and 0. So we still need to do that. So if I do that, well, you can see clearly that one row in this matrix is a multiple of another, right? So it is just the first row is minus 2 multiple of the second one. So clearly the determinant is equal to 0 because we only have one really row. The other one is will reduce to 0. Okay, so what's the solution? So we have two equations, two unknowns, X dagger, Y dagger, but we have only one equation to solve. So what can you see? So what's the solution? Well, clearly 0 solution, but we are not interested in 0 solution. So we can write all solutions in a parametric form, right? So, but so, all right, so we used A, B, so now it's C multiplied by what? 1 minus 1. No, 1. So it's clear. So 1 multiplied by 1 minus 1 multiplied by 1 is equal to 0, right? So be careful. So that's what it is. So this constant here is again a strange fact. We can set it to 1. So that's what we're really up to, 1 and 1. Okay? So, fine. We found the eigenvector, so I'll get rid of this scaling coefficient because we don't really need it. Because, the reason why we don't need it, remember how it works. We multiply it by something, and that something must be equal to 0. So, if in addition to that you multiply by C, well, you will be multiplying 0 by C. doesn't make any, well, it doesn't prove anything, does not make it any difference whatsoever. So therefore, might as well set C equals to 1 from the very beginning. So it doesn't really matter. As long as we have a right direction, 1 and 1 gives me the right direction. How long that is does not matter, because the length multiplied by 0 will still be 0. Okay? So here we go. So then, if we get rid of, so remember, the goal is to get rid of the left-hand side. So left-hand side is gone. That was a general theory. If we use a joint, then the left-hand side will disappear. That's how a joint was derived. Is that clear? So we don't care about writing anything in the left-hand side. It's going to be gone, because that is by design. That's how we design L dagger. So this matrix is designed from the very beginning to kill the left-hand side. It will be killed. No matter what, it will be gone. So therefore, I don't worry about that. So all I worry about this. So therefore, I have 0 is equal to these two products. Right? The first one is W31 dagger, and 331 is 1 and 1. Right? Remember, that's what that is. Multiplied by F31. What is F31? What did we choose? So we have 1, 1. So don't need comma. Multiplied by F31. So what did we choose for this example? What is it? 1 and 3. Minus K multiplied by, now let's see what it is. Multiplied by. K is multiplied by, where is that? That's my eigenvector, 1 and 2, right? So we have 1, 1, that is the dagger quantity, multiplied by 1 and 2. Agree? That's what we get. Which is equal to, so, oh, forgot one more thing. Sorry. Need to be very careful here. At this stage, if you make a mistake, then the whole thing will collapse. So, no. And what I'm missing here, see what I missed? X. Okay. So, matrix X, in this case, how does it look? So, what is the matrix? Just look at the notes so that you know what is what and what is where. So, what's matrix X? Find it in the notes on the previous page. 1, 0, 0. 1, 0, 0, 0. So just checking that you see it. Right? So, and what is the vector? So the vector was there already, so it is 1 and 2. Okay? So that's what we have. So let's do the multiplication. So it is 1 times 1 plus 1 times 3. This is 4. Minus k. So if we take this matrix and multiply by this vector, so what will happen? 1 times 1 plus 0 times 2. 1. And 0 times 1 times 0 times 2, 0. So the result of this will be 1, 0. So, and then we need to multiply it by 1, 1. 1 times 1 plus 1 plus 0, what it is? 1. So therefore it is just k. And this is to be equal to 0. What's k? K equals 4. So you see, we found it. It's the same result. So indeed, this produces what we need. So therefore, we should be happy. So now we have the method which contains or gives us the value of that constant. And that constant solved the solvability problem, and that constant feeds back to the amplitude equation, which is Landau equation, and which we solved in the beginning, and we know what to expect. Supercritical, subcritical bifurcation, depending on the value of k, whether it is positive or negative. So, yes, we sort of could relax and say, okay, we've done it. We achieved what we wanted. We have the method which produces everything. And that was the feeling people had 65 years ago. Okay? This theory is called Stewart-Landau theory. Stewart. So Katie Stewart is a professor in Imperial College in London, and that's attributed to him. He's about 94. He's still alive. And 2 years ago, I had an honor to present an online seminar on this topic, and he was in the audience. Okay, so the question is, so far, I just repeated what has been known for 65 years. What's the problem with that? Can you spot the problem with what we've just done? Logical problem. And I wouldn't be surprised that you might not see that, because people didn't see it for 60 years. So, to go beyond this point, we need to realize what we've done. So, what we are doing we are considering essentially a bifurcation diagram. So this is now our Reynolds number if we're talking about Poiseuille flow. And this is the sigma R value. Maximum sigma R value. So we are looking for the place or for the value of Reynolds number where the largest sigma R value becomes positive, or at least 0. And this occurs here, somewhere here. And we call it critical Reynolds number. And we do this numerically, right? You saw the code, I ran the code. How did I do that in the code? In practice. So here is you have the code, and all it does, it takes Reynolds number in and spits out all sorts of sigma values. And you look at them, and if I do not tell you where to look, you will start with Reynolds number whatever, 0. You get some trivial result. You get Reynolds number 10. You will get some non-zero result, but it will, all eigenvalues will be negative, and so on and so forth. So describe in your own words how you find the critical point. So imagine that situation. I give you the code. I erase that line which specifies Reynolds number is 5772.2. I just erase it and give you the rest of the code. What do you do with it? How do you find Reynolds number, critical Reynolds number? How do you find that 5772? Just the easiest way. So you have the code. How do you find it?
what? So we have to code black box, press the button, so supply the Reynolds number, press the button, get the signal.
So for the range of Reynolds number, we calculate the eigenvalue.
Right. Exactly. So what you do is essentially try and error, right?
You try, you see it is negative, so, and if it is negative, what do you do?
We do another set.
What you do, if you see that signal is negative, then what do you do?
Increase the Reynolds number.
Increase the Reynolds number.
And if it is still negative, what do you do?
Increase once again, right?
And eventually it becomes positive, and then what do you do?
The maximum of sigma becomes positive, then we stop there. And
So I got the maximum, which is equal to 10.
so the maximum is 0.
How do you find 0?
So I already computed something like 5, so I got negative, now it's positive, and the positive happens to be plus 10. What's next? So before that it was negative, now it is positive, so next. Find the middle value, right? You go backwards. And then check, and then you go either left or right, and until pretty much you converge, right? By method of bisection or division by 2, or some sort of extrapolation, interpolation, but basically you do that iteratively. And in the course of these iterations, it is guaranteed that you will step into the positive territory, and then you will have to come back. And the reason for that is that because the only way you can find 0 is that by finding something which is negative, finding something which is positive, and then 0 will be sandwiched in between. So you cannot approach it from one side, or well, you can, but that it is unlikely. So it is more likely that you will overshoot, and then will have to come back, undershoot, and then you will have to come back, but smaller and smaller steps. So essentially here, then there, then there, then there, then there, and eventually get it, right? So the bottom line is that if you eventually locate critical Reynolds number here, then by that time you already visited all these points. Okay, you already visited all these points before you were here, and in particular you visited these points. So you might be interested in what is happening practically, what is happening beyond this point, right? Because if sigma are positive, we know that Landau equation in that case will produce well, or physically we will expect that perturbation will grow, and will grow to a certain limit. We will be able to see that. So that's what you want. So this becomes point of interest. So Reynolds of interest will be somewhere here. Okay, so that's call it Reynolds number. So that's what you do. So you located this point, but it is not the point of interest. The point of interest is somewhere here. Agree? And we know that at this point, Reynolds number, sigma r is positive. Okay, so sigma r behaves like that. So it is already somewhere here. Agree? So, and in this case, if sigma r is positive, all that theory that we developed, does it work? Yes, it does. But do we really need to worry about the value of k? What did we do yesterday before we bumped into this necessity of finding k? Remember how the logic was. So we were trying to solve the system of equations, and we were happy if we can do that. And we only started worrying about the value of k when we found something wrong, so something does not work. Agree? So at what point did our procedure, original procedure, break? Where? Did it break here? Where did it break? What was the breaking condition? So what is the condition under which the theory or this expansion procedure broke for the first time? Sigma r is 0, meaning that we first encountered the breakage here at the critical point. Are we interested in a critical point, though? What's our region of interest, practical interest? That is our interest. And we might have been there already, and then we stated, oh, no, we need to come back to the critical point. We need to find the critical point, even though we are not interested in the critical point. We're sitting here, that's what we want, but we have to come back to the critical point and do this joint business at a critical point. See the breaking logic here. I'm not interested in what happens at the critical point. Why am I not interested in at what happens in the critical point? Because I already know what happens there at the critical point. At the critical point, amplitude of perturbation by definition is equal to what? What is it? Bifurcation point is the point when perturbations start developing. And bifurcation point where amplitude of perturbation is infinitesimal, 0. I know that, so it is of no interest or whatsoever. I already know what sigma is. Sigma r is equal to 0 there, but that's about it, because perturbations, that's what I'm up to, they're not going to grow there. Their amplitude will be 0. We will not be able to see anything apart from base flow. So I know everything. So why on earth would I go back? I'm interested in what is happening here, but the theory, the way we developed it, or the way it was developed 65 years ago, asks me to go back. Compute this value of k, so for whatever reason, and then try to use that somehow to derive that amplitude equation. But fundamentally, I don't need that point. I don't need any information from there. Moreover, I am already here, so at least I already solved linear stability problem at this point. I have already have all the information necessary at the point of interest. Is that clear? So that is sort of painfully clear, like from if you start discussing that logically. So, and of course, I'm not the first one to realize that. So that has been realized from the very beginning. And what do you think the solution was? The solution was, all right, we will do that exactly, but we will limit our range of interest. So therefore, we will do all this beautiful theory, all these derivations, adjoint, and so on and so forth, but we will not go there ever. We will stay here. That was really a solution for 65 problems. So we got the solution. We have this method, which is beautiful method, mathematically works, everything good, but we limit ourselves where we can apply it. We cannot go any further than that because it will not make any sense. So that's what was happening. So therefore, what we will try to do is the following. So we would like to say, all right, if we are interested in this point, fine, but we might be interested in this point. And if we're interested in this point, there is no logical reason for me to come back there. And then from here, try to extrapolate something there. Okay, so instead of going straight up, I would have to go this way, do something weird here, and then somehow come back there. And of course, if I go that way, well, obviously, well, it is intuitively clear it's not going to be accurate. So this distance is much shorter than distance this plus this. Agree? So if you want to go from here over there, so, and if you can go there, why would I go that way? Agree? So that's basically stuck in my mind from the time of my PhD, and I was just thinking about it, and then gradually I realized what is happening. So what is happening and how all this can be sort of fixed and understood. So, first thing is, like it or not, but this is an approximate theory. In that sense, that we are looking for the full solution, but we make a number of assumptions. One assumption is that we take into account only a single alpha value. Remember? Single alpha value. And the motivation for that, remember what it was. We say that sigma is a function of alpha, and all alpha values that, all modes with alpha that produce positive real part of sigma, all of them will grow, but some of them will grow faster than others. And the ones which grow faster, they will always win, and they will eventually dominate. Okay, so therefore, let's forget about everything else and focus on the one which has maximum growth rate, because that will be visible eventually. Everything will be subdued, everything else will be suppressed. Good. So that's already an approximation, right? So this is already an approximation. So we are not ambitious to get the full solution containing everything, absolutely everything. We are only limiting ourselves to the major contribution, okay? And the trade-off is that, of course, we can try to get the full thing using expensive computations, but that will take you a few days and probably a lot of time in terms of just writing the code and testing the code and so on. Or you have an option to get a very good approximation within a few seconds, right? It's just on your laptop, just in front of you, press the button, and 2 seconds later you see the picture. So what do you choose? 2 days computations and half a year of testing, or maybe a couple of days of programming and 2-second computations. So, all right, so that's basically the idea. So yes, so you probably choose this one. So at least to get first impression of what is happening, do sort of bulk studies, and then if you're really interested in details at a particular point, then yes, run your code, fully nonlinear code for that particular regime, for that particular point. You spend 2 days, but only get results for 1 point only this way. But that point is at least located properly. So that's one thing. Second thing, at the bifurcation point and before the bifurcation, you have the solution which consists only on base flow. There's nothing else there, right? So nothing else is there. So that's by definition. So base flow exists, and the only possible solution before the bifurcation point. Okay, so I'll draw another diagram. So now I draw a solution, and this solution looks like, well, like this straight line, and this is base flow. Parabola, right? So parabola changes somehow, but it is still is a parabola. So, but at this point, it will come parabola plus something else. Agree? And that something else starts growing. The further away from this bifurcation point you go, the larger sigma value becomes, the larger that thing which you add is going to become. Agree? So therefore, what I will show here is this diagram. So what you actually have after this point, you still have your base flow part of it, but in addition to that, you have something occurring around it. So it is like a cone. And the width of this cone becomes larger and larger and larger as you go further and further away. Is that clear? So because well, the perturbations grow and there are more of them. So remember, the perturbations, they look like that at the critical point, sigma r. And at this point, only one perturbation might start growing. But later on, you will get something like that. And if you go, so this is Reynolds critical. This is Reynolds 1 greater than Reynolds critical, and this is Reynolds number 2, which is greater than Reynolds number 1. See what happens? So it becomes larger, it expands. So therefore, the contributions of into the total flow, they will become wider, right? Wider range contributes to it. So that's why this circle expands. Agree? So we realize that, and that is physically clear, right? So further away from bifurcation point you go, the more and more contributions come in. But what about us? What are we actually talking about? We are talking about a particular component into this contribution. The component which is based on the eigenfunction of corresponding to this particular value. Agree? So it will be dominant, but it is just a single component. Is that clear? So that's what happens. So the range becomes wider and wider, but we're still considering only dominant contribution out of the whole range, but the range itself becomes wider. Is that clear? So therefore, what we are doing here, so essentially, because we are talking about only one point, we get only one point in this disk. Agree? That's what we are doing. So essentially, what we are doing, we are representing the whole disk with a single point. That's what we have. However, since the disk has a different finite size, it consists of infinitely many points. And those infinitely many points will correspond to essentially different initial conditions. Right? You have infinitely many options for creating initial conditions. So therefore, these points could be selected at will. So they will be in this disk, they will be just a single point that every time we do that, but we can control where they are. We have an opportunity of choosing the point of interest within this disk. And therefore, in other words, we are choosing this angle which connects the particular point with the origin. So therefore, we have these rays which going through these circles. Okay? And these rays which connect the origin or the bifurcation point with the point of interest, well, they form some angle with the axis. So this is the angle, right? So I don't know what theta angle, right? So this is angle theta, some angle. Agree? So that's what it looks like. So we are essentially trying to project the full solution, complicated solution, nonlinear solution, onto the space spanned by eigenfunction of the fastest growing instability mode. That's what we are doing. So now that I use the magic word projection, so how do you understand projection? Just in a common sense, what can you visualize it with? So at this stage, I will just open my slides, which I presented at that workshop, which I mentioned to you. And I will show you a very simple interpretation of the concept of projection. Okay, it's here. Is in your folder, so you will be able to get there. So I already said a few things here, so I will not go through the full pack, but I'll just refer to some nice pictures here to show you what it is. So a few images here. So what I'm talking about is shadows. So clearly what you see on a shadow depends on the position of the sun, right? The same shadow or shadow of the same object its shape, what it actually shows, will depend on the day, will depend on the time of the day, will depend on whether there are clouds or not. So all these are there, right? So, and the same object will throw different types of shades. So if you are, if it is just a post, so forget about the horizontal bar, and the sun is straight up it, can you see any shade? You can't. So this is the interpretation of a critical point. At the critical point, you cannot see any shade. It is too small. And then you start changing the angle. Sunset. Shadows become longer. And now you can judge some properties of the original object by looking at the shade. So, and that's what you are doing. So we are looking at this projection, eigenfunction projection, right? So therefore we are looking at the shadow of the flow, of the full flow. Full flow is much more complicated than that, but we are only looking at the shade. How useful is that? Well, to some degree it is useful because at least something can be judged from the shape of the shadow, right? Overall picture is clear. So this shadow tells me that the object has a stem, essentially a straight post, and has a bar and has some structure on top of that. Okay? What I clearly cannot say by looking at the shadow, what is it made of? Is it timber? Is it concrete? Is it iron? No, I cannot do that, right? So I need to come to the real object and touch it and see that. But I can see what its shape is. So clearly you can get some information, but not all information. And what you get, another thing, I just repeat, the important thing is that what you get out of shadow depends on how you create the shadow. So if you create the shadow from one angle, you might see one feature. If you create the shadow from the other angle, you will see the same object will throw completely different shadow. And by doing that, by looking at the same object or the shadows thrown by the same object, but from when the light source is located at different positions, you will be able to see different features of the same object. Agree? And by doing that, you might be able to get very good idea about the shape of the complete object, three-dimensional object, right? So it is possible. So, but to get the full information about the object, you need to essentially take this post, dig it out, take it to the lab, break it, see what's inside, and so on and so forth. Well, be my guest. Go to the desert and dig it out, right? So that's somewhere in, I think it is somewhere in Egypt. So, but if you just a surveyor, you walk around it, you look at it, at the shadow, well, you maybe spend the day there, so you observe what happens with the shade, and you cannot climb that post because it is too tall, for example, or you don't want to get electrocuted, so therefore you'd rather not to climb there, but you look, walk around it and you look at the shadow and you will be able to see quite a lot, right? So that's exactly what we are doing. So in this disk, these points, these are essentially shadows thrown by the full flow, but we can freely choose the position, and every time we choose the position of that single point, we see something different. Okay? But how much we can see depends on the length of the shadow, and the length of the shadow depends obviously on the size of the object itself and also on the angle, right? Angle of the light under which light throws the, source throws the light of it, so sun, where the sun is. Okay? The only thing is that in this example here, we have sun, right? And we cannot control sun, right? So we have to wait what happens. Well, the sun will do the things they want to do. But if we're in the laboratory settings, right, well, I can change the location of the lamp quite easily. It is my choice. And same thing with analysis. So I can change the angle under which I look at the same object at will. I choose it, how I look at this. And after this is done, I look at the particular features. And then when I'm satisfied, I move my light source and I look at other features of the same object, just not touching this object itself, but rather looking at its shadow. Okay, so that's the philosophical idea about what I'm going to tell you next mathematically. Okay, so let me just stick with these slides, and very quickly they just recap what we've done. So there's nothing new. It's just a summary of what we went through over the last few days. So these are our equations. This is our initial assumption. So our goal is to figure out what A is. We still don't know what A is at this stage. We know that this is eigenfunction, so but it is multiplied by periodic component. So we know that A goes to 0, and therefore we just say that the formal solution is like that. So then we assume that A is not infinitesimal, and we go through the procedure. So it is exactly the same what we've seen before, except instead of matrices X and Y, I have matrix B and A. So this is X matrix in my handwritten notes. This is Y matrix, and you can see that it depends on alpha, and pi. Pi in this case is representative of Reynolds number. Just forgot to change that, so it is supposed to be Reynolds number there. Okay, and we go through the process. So this is the picture for the Poiseuille flow. Okay, so that's we've seen this. What is it? Fixed. So that is as a function of alpha. So it is different. So they are shown as slightly different, but that's the same picture as produced by the code which I demonstrated. So it's just different version of this same picture. So we go through all this algebra. We introduce this quadratic null variation, so it is all there. These are recognizable equations, so A squared, A magnitude squared, so all this is there. So just we went through that. And looking for, so talking about those, so this magenta conclusion is the same as we made before. So we're just making conclusion that we can solve these operators are not singular. We can solve the problem. So we go to the third order and we still have no problem. And we have no problem, and that's a problem. So that's what this slide is about. So we are going and going and going, and we still cannot get a solution. Remember what we went through over the last couple of days? So we're making effort, we're expanding, we're substituting, and we still do not get a chance of finding what A is. So that's what this slide is about. And then we realize that we need to go back to bifurcation point, and that's what we have here. And we realize that K has to be introduced, and that's what we've done. And we consider the sigma r equal to 0 bifurcation point, and we will get the expression for K. So through these adjoint formulas, here we are. So we've done all of that. And this is essentially a discussion that we're having now. So we have this point of interest, Reynolds number of interest. So here it is denoted by pi, but in our case it is Reynolds number. And we would like to know what happens here, but we have to go back all the way to the bifurcation point, do something here, and then from there go back there and try to make a conclusion of what we see. And this is, of course, just does not make any sense. So that's the problem. So that's just a restatement of the issues, and because it is was a formal presentation, so I gave references to what people thought about the problem before. So some references here. So, resolving the problem now. So we stated the problem, we resolved the problem, but we got another problem, and now we need to resolve the next problem. So how do we find that constant k? Remember, the bottom line is that if you go back to the point, to the bifurcation point, then you have only one option, a joint. Okay, a joint formalism. But a joint formalism is only justified at the bifurcation point itself. And we don't want that bifurcation point. Right? We want to be at the point of interest, which is already beyond, and we don't want to come back. Is that clear? So therefore, if we don't want to come back, then there is no need for us to stick with a joint operator. Logically clear, right? So a joint operator resolves the problem, but we need to go back to the point, to the critical point. And we don't want to do that because, first of all, we know everything about what happens at the point there, on one hand. On the other hand, we are interested in something completely different. We are interested in the point which is beyond the bifurcation point. Okay? So we don't want bifurcation point because first of all, we are not interested in it. Second of all, because we know that amplitude there is equal to 0 anyway, so no point going there. Right? So therefore, that's what we are trying to resolve now. And that's sort of state of the art in the field. So how? Clearly, the condition that the solutions have to include a joint engine, a joint algebra, well, it's not necessary anymore. So what can we replace it with? And what we can replace it with is that with the idea that we would like to be able to choose our own point of view, or in other words, the location of the light source, so that we choose what sort of shadow we would like to explore. That's what the basic idea is. So instead of trying to go back all the way to the situation when the sun is straight above the post and you don't see any shadow, but so therefore, but still you will be able to do something with the joint operator. So what we try to do, we would like to have a sun in an arbitrary position, and we would like to be able to make sense of the shadow which is thrown by a light source located other than at the very top, somewhere here, or here, or here. That's what we are trying to do. So therefore, what we are trying, what control we have in our hands is essentially the choice of the angle, because projection is defined by the angle. Remember what projection is? Just very simple geometric interpretation of the projection. So if we have a vector, so this is my vector W, that's the full solution. And if this is my solution W11, this is my linear eigenfunction. So what I would like to do is to essentially project the full solution onto W11, onto this direction. Right? So therefore the shadow will look like that. That will be the shadow. Is that clear? Okay, by the way, how much time do I have? 5 minutes, yeah. So yeah, so we are well on track, so I probably will not need the full last hour to finish this discussion, so that's good. So, but I will need some of that. So that's what we do geometrically. So this is the full solution, but this is just eigenfunction W11, and we would like to represent our solution. So this is the perturbation. So we would like to represent our full perturbation by its projection onto W11. And this is the angle which enters the projection, right? So clearly W11 will be equal to W magnitude multiplied by cosine theta. Okay? Is that clear? So the degree of freedom that I have by choosing this light source is that I control this angle, theta. Geometrically, that's what it means. If I choose this angle, so therefore I will change this triangle, and I will be by changing the location of the light source, I change this angle theta, and therefore I will be able to see different projections of the full solutions. So that's the geometrical interpretation. Okay? Now, another thing which we need to keep in mind is the following. So the full solution that we write consists of A multiplied by W11 plus A squared, not A squared, so this is multiplied by E, this is multiplied by E, plus dot dot dot. Remember, that's our expansion, how our expansion is. So the perturbation, well, obviously we have base flow plus perturbations, but perturbations are expanded like a linear eigenfunction plus eigenfunction modified, one modification of this eigenfunction, and it looks like that. Okay, if you look at the formal expansion, you will see that that's what we have. Plus, of course, all other terms. Okay, so but let us look at what this means geometrically. So we have W11, which is this one. And to get the full projection, you need to stretch it, right? So if this is your computed vector, to get the right projection, you will have to stretch it. Is that clear? So, and this stretching coefficient is this amplitude. That's what that is. Agree? Okay. But how does that happen? So maybe I will just can stop here, so I don't want to break the logic here. I would like to just have it as a one piece of discussion, right? So let's stop here, and I will just do that after the break. So I will take it, probably will take me 15 minutes or so. Okay? All right, let's have a short break, and then I will continue.